Hello everyone. Today we're starting on the section called the Manhattan Project. This is a project which ended up creating the first ever nuclear reactors and the first ever nuclear bombs. We can see a photo of one of the sites in this photograph. Alright, let's get started. So the Manhattan Project was the project from the American government during World War II in order to build a nuclear bomb before the Nazis could. So physicists realized that the fraction of fissile uranium-235 in nature isn't large enough to cause an explosive reaction like you need for a bomb. So large factories were constructed, like the one in the photograph, in order to separate uranium-235 from uranium-238, which, as you can imagine, will be quite difficult to do, seeing as they're the same element. But it turns out that the very slightly different atomic mass means that it's possible to sort of sort it out a bit. Of course, you don't quite get pure uranium-235, but you get a much higher concentration than occurs naturally. So the idea of a nuclear bomb is to create a supercritical mass during the detonation of the bomb. And so this is achieved by taking two or more subcritical masses, so masses of a radioactive substance that haven't gone critical, and bringing them together. Once we have a critical mass, it means that we have enough fissile material for an uncontrolled chain reaction. In a subcritical mass, we can't get that chain reaction happening because there's not enough of this substance. So the subsequent chain reaction releases lots and lots of energy, because for every single part of the chain you get a large amount of energy produced, and you also get 2 or 3 more chains starting. So the critical mass of a sphere of enriched uranium, so the high purity uranium-235 that was created during World War II, is about 52 kilograms. So if we get a 52 kilogram sphere of highly enriched uranium, it'll be able to undergo nuclear fission in a chain reaction. For plutonium, whose atomic number is 94 instead of 92, the critical mass of a sphere is only 16 kilograms, so it can be a lot smaller than uranium. This is because it's a lot more unstable. So during the detonation of a nuclear bomb, chemical explosives are used to throw together different parts of plutonium or uranium to produce a critical mass. In World War II, there were 2 atomic bombs dropped. One of them used enriched uranium for its fuel, and the other used plutonium. So in a uranium gun assembly, what we have is something looking a little like this. We have chemical explosives that combust and drive 2 hemispheres of uranium together. Each hemisphere on its own is not of critical mass. So that means that you can leave it there as long as you like. You'll never get that chain reaction starting that will release more and more energy. But as soon as they come together in the middle of the bomb, it means that we have so much uranium that an uncontrolled chain reaction will occur, and we'll get a huge explosion. For a plutonium bomb, this won't quite work the same way due to the nature of plutonium and its instability. So for the bomb that was dropped during World War II, scientists produced a sort of shell of explosives, and the combustion of those explosives sort of compacted a little ball of plutonium inside it. It turns out that if you have a different density, you'll have a different critical mass, because a low density sphere means that it's very difficult for a chain reaction to start because it's all spread out. But as soon as it becomes very compact, because it's been, say, the subject of an implosion, we'll reach critical mass and get a huge nuclear reaction occurring. So in 1945, the 2 atomic bombs, one plutonium and one uranium, were dropped on Japan. We can see a photograph of one over here. So the enormous amount of destruction caused by these bombs was mostly unexpected. No atomic bombs had ever been dropped on a civilization before this point. The only atomic bomb that had been detonated before the ones that were dropped on Japan was an experimental plutonium bomb in the middle of the American desert. So each of the bombs detonated with a force of about 20 kilotons of TNT, which is quite a lot of explosive. The bombs killed hundreds of thousands of people, which, as I said, was mostly unexpected. At this time, it was unknown that bombs could do that amount of damage. One cause of death was the radiation produced by the bomb, as well as the huge explosion in the fireball. You had huge amounts of gamma rays and X-rays and so on being created by the nuclear reactions. So some effects of nuclear radiation don't actually show up immediately. They linger in a body and they can cause cancer decades after the initial exposure. Because of this, it's difficult to know exactly how many people were killed as a result of these bombs. Another possible effect of a nuclear bomb is fallout, or radioactive fallout. So this is the name given to the radioactive dust and ash left over after a nuclear explosion that gets propelled up into the atmosphere by the mushroom cloud. And the reason it's called fallout is because after it's been propelled into the atmosphere, it'll slowly fall out. And this process, because the pieces of ash and soot and dust are so small, can take a very long time, days or even weeks. So many negative things came out of the production of nuclear fission. We had the destruction of life during World War II. Another consequence was the production and proliferation of nuclear weapons, which just about everyone now agrees is a bit of a problem. And finally, we have nuclear power plant accidents and waste products. We can't figure out a way to get rid of all the dangerous radioactive waste products caused by nuclear power plants. And as we know, disasters such as Chernobyl or the recent tsunami in Japan have showed us that nuclear power plants, although quite safe, can still be the subject of huge explosions and catastrophes and things, which can cause large amounts of radiation to be released. But it's not all bad. The discovery of nuclear fission allowed for the use of a new, large source of electrical power. Uranium nuclear power plants require less fuel and are far more efficient than, say, coal power plants or natural gas power plants. They also produce less pollution during the process of burning the fuel itself. That said, it still produces a fair amount of pollution when we mine it in the first place. It gave us a better understanding of the nature of the nucleus and expanded our knowledge of the universe and exactly how it works. And finally, we can use radiation in things like medicine in order to get images like this of the inside of people's body. And this is in fact one of the more widely used uses of radiation today, aside from nuclear power plants. So that's the end of the theory. In this section we've learned about the Manhattan Project and the construction of nuclear bombs. Let's go on to some questions. Question 6. When compared to the critical mass of a sphere of uranium-235, the critical mass of a sphere of plutonium is larger, smaller, the same, or does not exist? Well, first of all, it's not D, because plutonium-239 is even more unstable than uranium. Our three options then are larger, smaller, or the same. Now, if they were exactly the same, it would mean that plutonium was exactly as stable as uranium, which we know is not the case. If plutonium was more stable, then it would need a larger critical mass, but that's not the case. If it's more unstable, it will need a smaller critical mass, and so B is in fact the correct answer. Question 7. What is radioactive fallout? We have a few options here. Radiation falling out of a nuclear reactor, radioactive material falling out of the sky, a falling out between nuclear scientists and the government, or neutrons falling out of nuclei during fission. Now, all of these do occasionally happen, but the correct answer for the meaning of radioactive fallout is in fact B. So during a nuclear explosion, we get a lot of dust and ash propelled into the atmosphere, and as that comes down, it can spread radiation a very long distance. Question 8. Why was so much time and money spent purifying uranium-235? Now, we know that in the first ever reactor, Chicago Pile 1, Fermi used basically natural uranium instead of enriched uranium. So we can get, to a degree, nuclear fission and a nuclear fission chain reaction out of uranium-238. But it's easier to get it out of uranium-235. So because uranium-235 is more fissile, it can be used in more applications, I guess, than uranium-238. And the example in the Manhattan Project was the nuclear bomb. If you had highly enriched uranium, then you could make the bomb weigh far less and actually be able to carry it over to the enemy or construct it properly. Question 9. Compare the yield of a nuclear bomb to that of a conventional explosive. And so the question here is, how strong is a nuclear bomb in terms of, say, tons of TNT? And I actually went through this in the slide, and so I'm sure that you'll recall that it's about 20 kilotons of TNT. Alright, so let's go into this in a little bit more detail. Question 10. TNT contains 4.184 megajoules, that is 4.184 million joules, of chemical energy per kilogram. The first nuclear bombs weighed about 4.5 tons. How much energy is contained in 4.5 tons of TNT? In other words, how much energy would have been released if the bomb that had been dropped on Japan was made out of TNT? So here we just simply take the mass of TNT and we multiply it by the energy per kilogram, and that'll give us 1.883 times 10 to the 10 joules, which is about 20 gigajoules. Quite a large amount. So, in a nuclear bomb, how much mass do we need to convert to energy in order to get this amount of output? So how do we equate mass and energy? Oh, that's right. The famous equation, E equals mc squared. So our energy in this case is 20 gigajoules. The mass is what we're trying to find, and c is the speed of light. So we can rearrange it so that mass is the subject of the equation. M equals E on c squared. Now we can substitute E and the speed of light for c, and we'll get an equation looking like this. We can use a calculator to find that, and it turns out to be 2 times 10 to the minus 7 kilograms. And because that's a little bit hard to visualize, I've got it in grams as well. 0.0002 grams. It turns out that the first nuclear bombs produced the same amount of energy as 20 kilotons, and when we compare it to this mass, it releases about, I think, 5,000 times as much energy. And bear in mind that this is a sort of sphere of uranium within the bomb itself. It's not the entire mass of the bomb. In fact, during the explosion, less than a gram of mass actually was converted into energy. Most of the mass that the uranium started with was just converted into other atomic nuclei. So it just goes to show that only a tiny amount of mass and a tiny amount of nuclear fission needs to occur to release enormous amounts of energy. Alright, so that's the end of the questions. In this section we've gone through the structure of a nuclear bomb and the energy released by a nuclear bomb and the catastrophic events that it caused during World War II. In the next section we'll be going on to some of the more beneficial uses of radiation today.